Yo, what's up, guys? I'm back. I have just finished my exam, so I'm officially on summer break. And so, I don't know if you guys saw my post, but I have completed my CPU. And before I showed off, I want to give you guys a video, kind of breaking down the parts of it, how I wanted to work, and my inspirations for it, just how it all fits together, just all the components of it. So my last few videos have been made about these components that are going to specifically be used for this CPU. So the first one is, of course, the RAM. So that 128 bytes of RAM that I made that make use of instant redstone to be very, very fast. Beautiful R right there. There you go, RAM. Now, the second component that I want to add is the ALU, which I made 2 videos ago, if I remember correctly. So we have our ALU, which can do 12 different operations here. So my ALU. And then finally, my most recent video was my instruction memory, which I'll put right here. So this is, again, this instruction memory can vary. Right now, I just have the 64 steps or 128 bytes memory unit hooked up, but I can obviously add more. But right now, I'm not doing anything with more than 64 steps, so it's fine. That can always change. So these are the major parts right now, or as of my last CPU. But I've actually been reading some books on CPUs in real life, like IRL CPUs, not Minecraft. And this one book I really like. It's called But How Do It Know? It's by J. Clark Scott. And basically you build a CPU. And I like it because it really simply explains it to you. So I mean you could go in knowing actually nothing about computer architecture, and I think you'll come out learning a lot about it. And so it showed me some better ways of handling stuff, within a CPU. And so one thing, I think the most important thing that I learned about is something called a register. So we'll put that right in the center because this is, I feel like, one of the more central things of the CPU. Register. So I'm only using 4 registers, so only 4 bytes of data. But a register is basically like a mini RAM module. And usually people say how RAM is like immediate memory, but registers they're almost more immediate. So what you're working with right away, because then this register can then go into an ALU or it can be outputted somewhere else. So they're like the most immediate form of memory, and they're usually really small. So no, not a ton of bytes, a lot less than the RAM. I mean, this is only going to be 4, but some can have 8 or 16. The second thing that I saw that I really liked was something called a memory address register, or MAR. And what this is it's basically just another register, and it saves the memory cell that you're accessing in RAM. So to pull something from RAM, it takes 2 steps. So one, it takes loading to the memory address register, so loading a number that could be from the registers themselves or just directly from the instruction memory. Um, and then the second step is either reading or writing to the RAM. Now, accessing the RAM takes 2 steps instead of one, like my last one, but it simplifies the movement a lot. So a CPU essentially is just moving bytes back and forth from one register to another. And so my last CPU, I had to constantly be increasing the amount of instruction memory so that I could be able to access the large amounts of RAM. And so this can fix it where the memory address could be one or a series of 1 byte registers that can access the RAM. And so then I can treat RAM almost as another register, like a fifth register almost. And so I can just pull from that. So I can load a memory address register and then pull from the RAM. So that just simplifies creating the codes. It simplifies the instruction memory. And one thing I like to bring up is that the instruction memory has gone from 32 bits to 16 bits. So I've halved the amount of bits that it uses. And so the third thing that I took away from that book was something called an accumulator. So we'll draw a little address right here. Accumulator, we'll write it as A. And so the accumulator is connected to the output of the ALU and normally connected back into the ALU. So the accumulator is basically just a placeholder for the data. So it makes it more, I can move it wherever I want. And when you try to memorize, try to set a register while enabling it at the same time, it messes it up, because whenever I try to set it, it basically clears the register, which then affects what it's enabling. So it's much easier to have almost like a step in between, so that I can let it reset, and then it's fully calculated, and then I can move it back into the register. So the accumulator is connected, this is the output basically of the ALU, and then is connected into the ALU, and then connected to everything else. And I'll start drawing the connections up in a little bit. One way I like to think about it is that the ALU itself isn't necessarily a register. When you want to add something, you move it through the ALU into the accumulator. So the ALU is more of the track almost. It's not like a register itself, but it's like a specific wire that the data goes through. There is a part of the ALU that's kind of built in, and it's called the temporary register. And so before I talk about this, I need to kind of explain how I've been adding in the past or doing any operation. So normally with operations, you have two numbers, except for a few like nodding or bit shifting or anything like that. But most of them require two numbers, two bytes of data. And so I saw a Matt Batwing's video where he had a layout of registers that actually could output two at a time. Now, I don't know if he did a tutorial on it, but I kind of just made up my design myself, which I think I got pretty close. But I kind of had the same layout where it could output two at a time. And so I'm like, okay, well, this could make my addition much, much faster. Or, of course, any other addition, subtraction, all those other operations, much, much faster, because I could just output two at a time. Now, that caused a lot of issues, because one, the RAM was basically twice its size, because it could output on the left or output on the right. So it had to actually memorize, or it had to set that data twice. So it would actually basically have double the size. And the second thing was time. Now, if I just want to draw a little sketch here. So if I had like 3 RAM modules next to each other, both with the double output, and then I have, my ALU over here with these 2 inputs, and I want to hook, I want to hook the left signals up together and the right signals up together. What I'd have to do with the left signals is, okay, I can do something easy, just like this, and then directly in. Now for the right, what I would have to do is I'd have to go through the left line. So go through the left line and then connect them up somehow. And then this has to kind of leap over here, and then it goes in. Now, and so I would make use of this through repeaters. Now, the issue with that is that it would cause a lot of delay. I need to use a lot of repeaters. So this actually made it a lot slower than it needed to be. So one thing that I saw was that most CPUs would use just one number at a time. Like I said, it's moving just a byte from one location to another location. So the registers or the RAM, wherever I'm moving it from, or directly from the instruction memory, I would move it into the ALU, and the ALU would have a temporary register. So if I want to add two numbers from my registers, I would load register 1 or move register 1 to temporary register, and then I would move register 2 to the accumulator. And so then it saves register 1 to temporary, and then the register 2 comes through and into the accumulator. And then of course I can move the value from the accumulator back into the registers. Now those were my major takeaways, but I am leaving out one important piece here, and that is the instruction address register. And it is again, it's just another fancy register that keeps track of what step I am on, what instruction I'm on. And so it's directly hooked up into the instruction memory, and this just increments by 1. Or if I want to do a jump or jump if, I can load something directly to it. So with all this out of the way, how would I wire this? Now, of course, I want my register to be able to move directly into my ALU. So that's good. So I can move my register directly into ALU. And then with my accumulator, I can move my accumulator directly into the ALU, because sometimes you want to move your output directly back. But then I might also want to put my accumulator right into my register, so then I can, have another line here going into my register. But I might also want my accumulator to go into my RAM. So how I would do that is I would, snake through these wires. So if I can just kind of go over this wire and then into the RAM. So we can do something like this. And then for my register, I want my register to go into the memory address register and also into the RAM. I also want my accumulator to be able to go into my memory address, and then I want my RAM to be able to output into my registers. I also want it to output into my ALU, so that's all connected up. And then the final thing that I want to do, or almost final thing, is my instruction memory. So it's going to output here and might come around here, and I want to be able to load it into RAM. I want to load it into my register, and then I also want to load it directly into my ALU, so I can do that. And then, of course, I want to be able to load everything into my instruction address register, so I can do some jumps. So we can that's a really bad drawn arrow. And then we can load this in. I want my RAM to go into my instruction address register. I also want my accumulator to go into my instruction address register. So that is everything. It's all wired up. It looks beautiful, doesn't it? So of course, this would get very hectic very, very quickly. So instead of having individual wires, I tried my best to make use of a concept called the bus. So by making use of something called a bus, I can make this look a lot neater. So a bus is essentially a major wire that can go both ways and connect anything. So almost think about it like a highway, like a state highway. And so it connects everything up, makes it a lot easier. So there's not little mini roads running everywhere. Um, and so this is more difficult in Minecraft because major components like repeaters or comparators are one way. So I'm going to have to restructure this a little differently by having almost two wires kind of close up next to each other. It centers mainly around the register, so all the outputs kind of feed into this register over here. Um, and then the output kind of comes over here. So it's a little different in Minecraft, but this is kind of the general look of it, where everything is kind of condensed into one or two wires, and that makes it a lot less messy and a lot easier for me to build and wire up. Now, of course, the major thing that I need to make is the control unit. Now, the control unit is exactly how it sounds. It just controls basically every aspect of the CPU. So it takes an input from the instruction memory, and so it's basically connected up to most of the CPU. And so that way it translates the ones and zeros into functions, into actions. So in a sec, I'm going to go a little more in depth into the control unit, but this is kind of the general layout. I am going to adjust this a little bit in my actual design to make it a little more easy in Minecraft, but this is the general layout. This is my little spreadsheet that I use to keep track of the values of everything and being able to code it easily. So the major functions here are move, load, and jump if. So like I said, the instruction memory is 16 bits. It's kind of broken up into 2 bytes, and each byte is just broken up into 4 bits. So the first move register, byte 2 is really where the function is. So the first 4 bits, these are kind of the function bits. The last 4 here are kind of variable. It depends on what it's doing. So, but the first byte 1 in this case, the first 4 are the register that's going to be set, and the last 4 are the register that's going to be enabled. So the first 4 are where it's going, and the last 4 are the starting point, where you're pulling the data from. Now, loading is number 2. It's function 2. And so in this case, the last 4 bits here are being used, and that's the register that you're setting. And so load is basically where you take data from the instruction memory and directly put it into a register. So these 8 bits are kind of going to be together. This 1 byte's going to be all together. That's your data. And then your last 4 bits here are where you're putting it. The jump if is kind of a 2-in-1. So the jump if when I was working on it, so the jump if is number 3. And when I was working on it, I realized that there's going to be 2 scenarios. The first scenario is I want to do a jump if, and I want to, if it is true, I want to jump to a value that is stored in a register. So I'm like, all right, that's easy. I can just make an enable. So these 4 bits enable a value and send it to the instruction address registers by default. And the second scenario was, what if I wanted to load that jump? And so I wanted to load it directly from the instruction memory. So that kind of got me thinking, okay, how can I do this without, messing them up? And what I concluded was that I can keep this here. I can keep this as the enable, so that's the enable register, and these 8 are going to be whatever you're loading. So if I were to load from a register, I just leave that all 0 and put in my register here in these last 4. But if I wanted to load from the instruction memory, I put my combination in here, and then over here, what I do is I can't give it 0, 0, 0, 0 because that's actually its own register. What I do is I give it a register that it doesn't know. So I could fill it up with all ones. Technically, I could give it a 10, but here I just give it a 15 just for simplicity. But if you give it a register it doesn't know, it won't enable anything. So that way I can kind of make it a 2-in-1 function. It's a little messy, but that was my best solution. And then input and output's pretty easy. It just input where I'm setting it, and then output is here. This is these last 4 are where I'm enabling from, and then these 2 are which output I'm sending it to. Now, what I was talking about with 2 control units is that was kind of my first control unit, where it decodes the signals, and then what it does is it unlocks a series of parts of the computer. One of these is a almost second control unit, and this takes the data and turns it into a register signal. So then it decodes it. So I can give it a 0, I can give it a 6 or whatever, and it will unlock that certain line. Now, why some of these have a star next to them is because some of these are only a set. So the memory address register, I never need to enable it or unenable it because it's always enabled. Same thing with temporary, same thing with instruction address register. And this is my function. So my ALU has several different functions, as you guys saw. And so I need to choose which one I'm using. And as you guys can see, I don't have an add or subtract function for the CPU. So what I do is I load a value or move a value to this new function register, and that chooses which function to use. And I have a ALU list over here and showing the binary digit and what function it correlates with. So that was kind of my thought process going into making a CPU. I kind of had to restructure it a few times to get this layout, but as you guys see, it's fairly simple. I mean, this only has 3 major functions, and you really just kind of have to stay organized when making them. But yeah, so I'm excited to demo it next video. But for now, that's about it. Peace.